All right. So yeah. So hi everyone. So before we start with this week's presentations, let's let me ask for kind of a few logistic things first. Logistical questions. Um, so first of all, if do you have any feedback from any of the notes or videos? So I started an anonymous feedback thread, but only one person gave feedback so far. So if you have any, kind of complaints or requests or anything like that.
Did people edit the response?
People edited the response?
Oh, I don't
Okay.
know. I was proposing that as a possibility.
Go look. I don't see.
No, there's
Um,
no history, it looks like.
okay.
Yeah.
Yeah. So just I guess post more follow-up discussions there, and you can just be totally anonymous. So long as you choose the right setting, then I can't see who you are either. And so that's that. The idea is that if you have any complaints, especially negative ones, you might not be willing to say them to my face. So then that's where you should put them. I do kind of want to hear about them, so don't hide it. Yeah. So well, that's one thing, and I guess another question is, so next week is reading week. I think we're going to respect that, so we're not going to meet. I don't know how serious Waterloo is about it this time, but in any case, it seems to be on the calendar, so we're going to respect it and not meet. So our next meeting will be in 2 weeks. And I was wondering, if you had any preference content-wise for what we should cover next. So I kind of realized that all the things I want to cover, kind of sort of won't all fit in this course. There's too many things to cover. So, I wanted kind of feedback from you guys about what we should prioritize. The notes are already, I think, somewhat long, and the readings, of course, are also, 3 a week. And even with that, I don't think we're gonna cover everything that we could. So, we have to choose which topics. Yeah, so I kind of wanted feedback from you guys about what you want to get out of the course, what material is important to you, if anyone has any preferences.
Do you have some? Could you list out some of the options?
Yeah, for sure. Yeah, so some things. So right, so some things we could cover. So we talked a bit about polynomial methods for lower bound techniques. I sort of wanted to cover adversary methods, which are sort of a different way of doing quantum lower bound. On the algorithm side, we only kind of did basic algorithms. I thought it makes sense to cover quantum walks, although we won't do a really thorough treatment because in part because I'm not actually that much of an expert on it, but we will do kind of a basic introduction to quantum walks, and we will, probably I won't. I'm probably not willing to skip over that one. So we're probably going to do a cover quantum walks and do some readings on it, and I'll post notes as usual. One thing we could cover or we could skip is learning graphs. It's kind of another way of designing quantum algorithms that's more query specific. It doesn't generalize much outside of query complexity, so maybe that makes it less important. Okay, well, that in any case, I don't know if we want to cover it or not, but we could. So that's an algorithm technique for quantum algorithms. There's stuff in communication complexity. So there's the approximate log rank or gamma 2 norm and related lifting theorem that lifts from sort of approximate degree in query complexity to approximate log rank in communication complexity. So that kind of stuff, that's a quantum communication complexity lower bound technique. It's how to show there's no good quantum communication protocol. Another one is quantum information cost. It's like another sort of it's a quantum information way to lower bound quantum communication complexity. That's something we could cover. It's kind of very modern and hot right now, but it's also extremely messy. Like it's just notationally, it's a big mess. So there's good sides and bad sides to that. More things we can cover. So all those are sort of kind of individual techniques, but there's sort of from the overall big picture kind of things. There's just papers about, let's say, the largest possible separation between randomized and quantum query complexity, or a separation between BQP and pH, which is basically a query complexity result, or how to convert a separation for partial functions into a separation for total functions. That's kind of a query technique that's used a lot. So it feels like something we should be covering in a course called Quantum Query and Communication Complexity. So just kind of big picture questions, like what the largest possible things that separations we achieved in this field. It just seems like a topic we should cover given the title of the course. So those are the things I had in mind already. I think they don't quite all fit, but they almost do. And then we can also go with any other ideas that and if there's anything that you want covered.
Let's see.
Maybe make this as a poll on Piazza. That might be a little bit better way of getting.
Yeah, that makes sense. Okay, we can set up a poll on Piazza. Okay, but does anybody have more options that should go on the poll? I mean, does anybody want to, know something that they want that should be covered? So, I mean, for example, how much communication complexity should we do compared to query complexity now that we've kind of done an introduction to it?
I mean, I would enjoy seeing one or two maybe lower bounding techniques that apply primarily to communication complexity. And that's enough for me.
Yeah, I mean,
just
we
a
only
basic
have
idea of how one might do it.
Sure. Yeah. Sure. Yeah. Yeah, makes sense.
But I would also like to see these complexity class separation with Oracle stuff.
Okay.
So I think I have a preference more toward that than the communication complexity personally. Like if one or the other had to be chosen.
Okay. Yeah. I can try to set up a poll if other people should also feel free to speak up if anybody else wants to voice an opinion. The problem with the poll is that, of course, I have to choose the questions in advance, and so it's like this is sort of an open-ended question, right? And then with the poll.
I mean, if a poll on Piazza, people can add something in the comments, right? Or
yeah, I guess
kind of leave it open like that.
Yeah, that's right. So I guess I can have a poll and have people put comments. Honestly, I haven't gotten a ton of engagement on Piazza so far, but yeah, but yeah, that's worth a shot. Yeah.
And for the what's that called, the graph learning stuff, maybe that can just be left as a final presentation option. I don't know if it's able to stand alone on itself enough, or.
Yeah, I mean, we can do something like that. Yeah. So I mean, sure. So not have that be kind of a full topic, but just kind of mention it, see if anybody wants to do a project on it or something like that. Yeah, we could do that. Okay. So next week is reading week, and after that, so I think we need to start thinking about projects. So as so the projects should be generally either individually or in groups of two. I guess if for parity reasons, if somebody can't find a teammate, I mean, maybe we can allow a group of 3 in an edge case. But yeah, so generally, I don't know. In the past, I've had different experiences for how often students want to pair up and do group projects versus work individually. I do expect kind of a larger project from a team of 2 than from an individual. So I mean, there is a sort of it's not like yeah, it's not strictly better in a sense. So yeah, I don't know how much. So you should find teammates through Piazza if you don't know other students, of course. But yeah, so it's up to you whether I don't have a good sense for your preferences, whether most people will prefer to work alone or most people will immediately pair up. So I don't know what you guys prefer. Yeah, and so what I would suggest, so the final project will be sort of what I hope for you to do is to kind of pick an open problem, maybe one mentioned in some paper, and kind of so first to write some background, why this problem is important, what are possible tools we could try to use to attack it, what are all the past research that's been done on it, and then try to work on it yourself. So I think part of taking a grad course should be about getting to the edge of the frontier of research. So working on an open problem, I think, is a good kind of goal for this course. You're not, of course, you're not required to solve it, but that's a bonus if you do. It happens. You shouldn't dismiss that necessarily, depending on how big of an open problem you pick. So it's good to try though. So you can describe kind of do a literature review about it, and then and then describe your attempts. Describe what what you tried, or why it doesn't work, things like that. So the total, I mean, and you can, so most of the report, it's fine for most of the report to be the review part. I was kind of hoping for maybe 8 pages or so as kind of as a rough target length, which is, it's not very long in the LaTeX formatting. I mean, the single column LaTeX thing, it's really it's if you haven't written in that format before, it's probably less long than you think. But yeah, that's kind of where I was roughly, I would roughly picture it. And longer if you're a team of 2, then I would hope that it's at least 50% longer or something like that. I don't think length translates 1-to-1 to effort, so I don't necessarily need to be exactly twice as long or something for a team of 2. But somewhat longer. And in addition, we're going to have some presentations near the end of the course, near the kind of last week of classes. We'll see how it goes. I might ask you to pre-record them so that it's kind of easier logistically, so we don't have to meet for too long in a live meeting to fit everybody. But I'm not set on that 100%. It's kind of it depends on scheduling a little bit, how much time we have to schedule and whether we want to meet live further or not. Yeah, so I kind of want you to start thinking about projects, and I'll post maybe some. Well, I'll try to have a Piazza thread to kind of have people discuss. Ask questions about the project, and in terms of your project topic, you should basically email me about it, or actually a private post on Piazza is maybe preferable, so then it's all in one place for me. So the idea is that you should pick a topic, and and a teammate, and we should try to get that done by the next time we meet after reading week. although I suppose it's possible for it to go a little bit longer. So, I'm just kind of hoping that you guys will start thinking about it. And a good place to start is just from something from the readings we've done so far, or the readings that I'll post for the coming week or 2 weeks, I guess. So you can look to see what open problems are mentioned there, or mentioned in my notes, for example, or anything else that you find that interests you. And if you want to do a project on some topic but can't find a good problem, then you can email me about that as well. So just or private post on Piazza, I suppose, is always slightly better for me. But if you don't like Piazza, then email's fine. So start thinking about that. Keep an eye out for project topics, something you might want to think about, and a problem you might want to think about, and also something you might want to write a literature review about, basically. So those are sort of the and again, there'll be some kind of short presentation that you'll do near the end of classes, and the report itself will be due at the end of exam period. So that's several weeks after. So most people, actually, usually the way it works is most people don't have their project fully done when they present. So that's how it goes. Okay. So any other questions on that, or on the any of the things we mentioned so far? Okay, let's figure out volunteers for, I guess, 2 weeks from now, for presenting from 2 weeks from now. I guess I didn't post the readings yet. I'll post them soon. So I know, so Joseph volunteered for the week after this time, but the week after this one is reading week, actually. So I was wondering if Joseph can still present the week after next, if that works for you. Sorry?
Yeah, I can still do that.
Okay, sounds good. So I'm putting you down there for, I guess, what is it, February 22?
Yeah. What's the topic?
Yeah, what the next week's
tentatively?
topic will be?
Sorry?
What's the rough topic for 2 weeks from now?
Yeah, so, well, I was open to changing it depending on feedback from you guys. I was thinking of just doing, the adversary methods as kind of a, another lower bound technique that kind of, it's in the same type of thing as the polynomial method, in that they both lower bound quantum query complexity. So that's kind of where I was thinking of doing in the next, well, I guess it's 2 week period now. One of them is reading, which is supposed to be a break for you. So that, but I was open to changing that. If people really want to cover something else.
I mean, I'll volunteer regardless if there's an open slot.
Okay, yeah. I'll put you down. But does anybody have opinions about what should be covered specifically in this coming period of 2 weeks?
Mostly asking because there's a couple paper in QIP I was interested in. If we're doing communication next week, or at some point I kind of want to volunteer. But yeah, anyways.
So you want to present on communication, you said?
Yeah, there's a couple of interesting paper I see in QIP that I guess I'll post on Piazza about suggestions.
Yeah. Why don't you post that on Piazza? Yeah. So we have to. Yeah. Are you officially taking the course?
No.
No. Okay. So yeah, we'll also have to see for scheduling reasons, actually. So right now, it's looking like the schedule is a bit full for presentations, but we may be able to fit you in.
Okay.
So it sounds like you prefer to present. So in that case, we'll try to fit you in. So.
Okay. Thanks.
Yeah, so I'll keep you in mind, and yeah. Okay, cool. Right. So I guess we have 2 volunteers now. So we, I guess I want a 3rd volunteer for 2 weeks from now. Somebody who hasn't presented before. Let's see. Well, okay. Some people are not here, so I don't want to kind of volunteer people only because they showed up. So if nobody wants to volunteer, I'll have to kind of do it offline and pick somebody randomly and send them an email. Okay, sounds like nobody's jumping up to volunteer, so we're going to do that. That's fine. So so far everybody's been very kind of responsive and you know and happy to agree to when I pick them. So that's great. And thanks to everybody for that. Okay, and so I guess we should go for the presentations now. So let's see, who should we start with again? Hold on. Sorry. Okay. Yeah, I suppose it doesn't matter all that much because the papers are sort of unrelated to each other in a sense. So who then do you want to volunteer to go first for this week's presentations?
I can go first.
All right, go ahead, Natalie.
Let's see.
And sorry, which one are you presenting?
Here, wait, can you see my screen?
Yes. Great.
Okay.
Yeah.
Yeah, so I'm presenting this 2018, I think, paper by Bunn, Kothari, and Thaler called "The Polynomial Method Strikes Back Tight Quantum Query Bounds via Dual Polynomials." And as like the name implies, it's using dual polynomials to prove quantum lower bounds. So this paper actually kind of does quite a bit. So using this method, they prove like new lower bounds for all these different problems here. So I guess briefly, I'll go just define what these problems are. So most of them can be characterized by taking an input of like n different elements. So it's a list of n elements, and each element is in the range R. And Fi is the frequency of some element I. So like any element I in R, how many times it's in the list n. So surjectivity is do all range items appear at least once? And yeah, so the new low bound proved was n to the 3/4 up to log factors, and it matches a previously proved upper bound, so it showed that it was tight up to log factors. And then K distinctness is, does any element appear more than K times? And image size testing is it's pretty similar to surjectivity, but it's a promise problem. So it's either all the elements appear at least once, or at most gamma times R appear. And it turns out that this lower bound implies like reduces to, you can reduce it to these 3 problems here, and also prove like the same lower bound for those problems. So statistical distance is you interpret the input as a probability distribution. So basically you look at the frequency of any element, and from that you get like the probability of that element. And so the statistical distance is what's the statistical distance from uniform up to some additive error. Shannon entropy is the Shannon entropy of that same probability distribution that I mentioned for statistical distance. And then there's K-junta testing, which is defined a bit differently. So you consider the input as like a truth table to some function. And the question is, does this function depend on at most K of the input bits? or it's epsilon far from any such function. So it's kind of different, but it turns out these three are all can be reduced from image size testing. And actually, this is supposed to be a K. Whatever. Here. Okay. So as we learned this week, approximate degree of a Boolean function is the least degree of a real polynomial, such that like the difference between the polynomial evaluated at any point minus the actual value is the absolute value of that is bounded by 1/3. And also, as we learned, the quantum query complexity is lower bounded by 1/2 times this approximate degree. So sometimes it's easier to prove a lower bound on this than like the direct quantum query complexity. So yeah, this method of lower bounding the quantum query complexity with the approximate degree is called the polynomial method. Here is just a summary chart I took from the paper that shows the improvement from previous lower bounds to the ones they proved. And you can see like some of these are pretty tight for the best known upper bound. Okay, so the main strategy used here is the method of dual polynomials, which I don't think they were in the lecture video, but they were like towards the end of the note for this week. So basically you can construct finding the approximate degree of a function with a linear program. And in some cases, it's easier to find a solution to the dual of that program. So that's sort of this method. So this is how the paper's notation defines the dual polynomial. It's slightly different from the paper, but pretty sure it's the same like idea. So a dual polynomial it's a Boolean function that takes in n bits, and it witnesses the fact that the degree is lower bounded. The approximate degree is lower bounded by d if this first case is called well correlated with f. So yeah, when you take a sort of kind of like an inner product with this polynomial and the actual function, it is at least epsilon or greater than epsilon. And then it also has one norm of 1. And in the notes, this is sort of like mentioned that you could kind of interpret this as that this psi is like a probability distribution over inputs. And then the last condition is that any polynomial with degree less than d has basically like no correlation with this function's psi. That's our witness for the approximate degree, and this is called pure high degree, at least d.
Yeah. So just this is small note here. The range of psi should be, I guess, the interval -1, 1 instead of the set.
Oh.
Yeah.
Yeah, thank you.
It's it's not Boolean valued. It's a real number valued, I guess. Yeah.
Right. Okay, thank you. Okay, so some nice properties of dual polynomials are that the first one that they mention is that it's lossless. So it provides a tight lower bound on the approximate degree. And then also, like historically, it's been well suited for analyzing block composed functions. And block composed functions are, so if you have like, so f is your block composed function, and you can define it as block composing g and h. And basically, you kind of split up your input into a bunch of blocks, and h is applied to each of the block, and h outputs a single bit, and then g evaluates on that however many blocks there are now, there's that many bits. So that's what block composed mean. And the paper just mentions that in Cite's previous work, that if you have such a block composed function and you can get the dual witnesses for each of these functions, then you can combine them in a clever way to get a witness for the overall function f. So here's the overview of kind of, since there's so many different problems that this paper finds a lower bound for, this was kind of their like map for how it all came to be. So the inspiration was a new way to show the surjectivity upper bound, which kind of inspired improved surjectivity lower bound. And then by kind of using the same proof strategy, they were also showed k-distinctness and image size testing. And then, as I said before, image size testing reduces to these three problems. So because the paper was so long and because the inspiration came from surjectivity, I kind of decided to focus on a sketch of the proofs for the surjectivity upper and lower bound. So that's what I'll show next. So just to remind everyone, surjectivity is given n items from a range R. You need to decide, does every range item appear at least once in the input? And like clearly the input's actually like a bit string that its length n times log R, just kind of assuming that R is a power of 2. So it actually turns out that for quantum query complexity of this problem is linear. It's like type big theta linear. But in 2015, Sherstov, I think is the author's name, showed that he actually upper bounded the approximate degree of surjectivity to n to the 3/4. So it shows that the approximate degree and the quantum query complexity aren't like this exactly the same. The approximate degree is actually lower. And then this paper shows that this lower bound is tight. But this paper also shows this upper bound, but in a new, like more simple way. So here I'll kind of show the sketch of that without hopefully going into too much detail. So the upper bound is was originally proved by Sherstov in 2015, but this paper, I'll show their simpler example. So the key to this is kind of splitting up all the inputs into ones that satisfy the following condition and ones that don't. So the condition is that every range item has to have frequency at most t for some specific t that's much less than n. And so let's define this curly C as a set of all inputs where this condition is true. And so phase 1, we're just going to pay attention to all these inputs in C. So we just want to make sure, we just want to construct a polynomial of degree n to the 3/4 that approximates surjectivity, but we only care about on these inputs. And so this was, apparently this is not as hard to do. I don't know exactly how you do this construction, but you could do this. So so then the only issue is that on the inputs where x is not in C, p of x could be like massive, could be exponentially large. So then we, in phase 2, we construct a polynomial Q that targets specifically these inputs x that are not in curly C, and makes them exponentially small to cancel out how big they are in P. So specifically for all the x that are not in C, we set that Q of x is much less than 1 over P of x. And then on all of the inputs where they are in C, so they do satisfy that condition, they're close to 1. So that when we take their product, it still approximates surjectivity on all the C that satisfy the condition. And it's exponentially small for all the C that, all the, the X that don't satisfy the condition. And yeah, and this is nice because I'm sure you guys know that when you multiply two polynomials, the degree is at most the sum of the original polynomials. So the degree is still going to be upper bounded by n to the 3/4. And then so the next part, I don't really know exactly how it works. If anybody else does, that'd be helpful. But next is there's what they call an averaging step, and this approximates this allows it to approximate surjectivity on all inputs, not just the ones that satisfy condition 1. So yeah, I'm doing a lot of hand waving here. Yeah. Okay, so I'll move on to the lower bound unless anybody wants to interject.
Yeah. Well, sorry, can you scroll up to condition 1 again for a bit? Yeah, I see. I guess I don't remember how they. It's presumably. Yeah. Okay. Sorry, I don't remember enough about this paper anymore. Okay. So yeah. I guess can you do the second part quickly, because I guess we're running low on time. Sorry, I was taking up a bunch of time at the beginning.
Yeah, I can just kind of do a high level. So the next part is the proof sketch for the lower bound, which is like novel in this paper. And for the first, most of it actually copies a previous result by Bunn and Thaler in 2017, but at the end they kind of just note that something can be improved, and then the bound is much better. So the stage 1 is you can reduce surjectivity to a block composed and an or. And then the second stage is proving a lower bound for just, and the and or has a promise that the Hamming weight, that's what I mean by this, is bounded by n. And so stage 2 is you just prove a lower bound for this. And basically the method uses kind of what I was mentioning earlier, where you can find the witness for and the witness for or and combine them. But this one doesn't satisfy and or with the promise. It just satisfies and or. So the step 2 here is a bit more involved, but it's post-processing this dual polynomial so that it makes sure it doesn't exploit any points that are not promised. So you have to kind of move those points to 0. And basically the first paper that proved that like n to 2/3 lower bound showed that psi almost ignores these inputs already, because if you look at the witness for or, they show that it's kind of like has decay as you increase the Hamming weight, and that's kind of what this shows. And basically the improvement was found in this paper by noting that the decay is actually exponential, not this like polynomial, for like once t is sufficiently large. So yeah, basically I guess I'm going through this quick, but this paper kind of noticed that the specifically for this or function, the or function is the bottleneck, and it's like even more of a bottleneck basically than the previous paper thought. Here's sort of like the quote from the paper that I thought was kind of helpful in understanding from like a high level. Yeah, so any low degree polynomial is, yeah, I guess you guys can read.
I think any low degree polynomial P.
Wait, sorry, it's even if the range is exponentially large. I just want to make sure. Sorry, the absolute value of p of x. That's a range,
Yeah.
right? Okay, just want to make sure. Thanks.
I mean,
Yeah. That's the So p is what's approximating this OR n.
Mhm.
And you only require that it approximates OR n for the low Hamming weights, and this is basically saying that even if you allow it to blow up outside of the range you care about, it still has to have high degree.
so
I think that's my interpretation.
the high degree depends on t, presumably, or not.
Yeah.
I guess it also depends on what they mean by exponentially large. Like if they just have a bound that's, is their bound kind of
yeah, their T is specific. That at least in this section it wasn't like entirely detailed, but they said it was for a specific T.
Oh, I see.
Yeah.
I see. Okay, yeah. Yeah, sorry, I don't know more about this paper. I read it a while back, but it looks like I forgot most of it. Okay, yeah, thanks. Right. Any more questions for Natalie? Yeah, so I guess I'll mention a few things. So yeah, so well, for one thing, the reason this paper is titled "The Polynomial Method Strikes Back" is because for a while, quantum lower bounds were basically mostly proven by the adversary method, which I guess we'll talk about in this next two-week period. So and many adversary lower bounds are very easy to prove, and so kind of it's a very nice, useful technique, and it seemed to kind of supersede the polynomial method, even though the polynomial method was historically earlier. But there's limits to what you can do with, I guess, at least what's called the positive form of the adversary method. And the negative form is very hard to use. So there's kind of limits to what you can do with adversary methods in practice. And this paper was saying, look, if you do the polynomial method with, with these dual polynomial techniques, then you can prove things that that you couldn't prove with just the adversary method, and that's kind of their list of results is all stuff that you couldn't prove with the adversary method. So you really kind of need this technique of dual polynomials, it seems. Yeah, dual polynomials themselves, I mean, it's kind of it kind of comes from linear programming duality, but it turns out that many measures in query complexity and even in communication complexity can be written as linear programs, especially kind of randomized measures. Like suppose you have randomized query complexity or something, then this is a probability distribution over decision trees. The probabilities in the probability distribution, the probabilities themselves, you can think of them as variables, and then if you say, okay, I want a randomized query algorithm that does something, then the constraints on what it has to do turn out to be linear in these probability variables. Like there are going to be linear constraints in the probabilities. And so you basically just get a linear program and you can take a dual. And the dual is often an interesting object. So depending on what query complexity measure you look at, you can often write it as kind of a program and take a dual. And I don't know how much background people have for these LP duality, and but yeah, so this is often a very useful thing to do because the dual objects, if you find a feasible solution to the dual, it gives you a lower bound on the primal. So if you find any kind of feasible solution to, say, this dual polynomial linear program, then you immediately know that the polynomial degree is at least whatever objective value you had there. And so this is the kind of the technique that they use. So specifically I mean, often the dual object looks like some kind of hard distribution. It looks like some kind of distribution over the inputs, such that it's hard to compute the function against this distribution. So, you know, of course, the primal object, the object you're constructing, is usually some kind of randomized algorithm of some kind, or I mean, it's well, sometimes quantum or polynomial or whatever. But the point is that you are taking linear combinations or over some objects that computing a function. So like, for example, probabilities over decision trees. So these are linear combinations of decision trees, basically. You know, here in the dual, you'll have the probabilities will be over the inputs, not over kind of the decision trees. And for polynomial, something similar happens. So in the upper bound direction, when you're building a polynomial computing something, you have a linear combination over monomials. You have right, you have kind of coefficient times monomial plus coefficient times monomial. You have linear combination over monomials. If you treat your coefficients as, you know, variables in a linear program, and you take a dual, you will get basically a linear combination over inputs, you know, which basically gives you a hard distribution over input, but it turns out to have signs, like it has plus and minus signs. And so it's not really a distribution. And, you know, the way I like to interpret it is that it's both a distribution and a modified function. Like it's a vector that has these positive or negative entries, and their absolute value sums to 1. So if you separate this vector out into its signs, like the pluses or minuses, and into the probabilities, basically, with the absolute values, which sums to 1, then you get a probability distribution over input, and you also get a modified function. You know, and so the object, the witness that there is no polynomial of low degree computing this function, the witness ends up being this pair of a modified function and a probability distribution, such that some conditions hold. Like in particular, the modified function has to correlate with your original function, has to look similar under this distribution. And the second constraint is basically that the modified function has to have what's called pure high degree. Basically, no monomial can approximate it even a little bit. It's kind of completely uncorrelated with every low degree monomial against this distribution. Anyway, so that's the technique of dual polynomials. It's kind of comes up a bunch in recent papers in kind of practice when you try to do lower bounds. It's still kind of, unfortunately, it's still a bit of a mess to work with. But you know, it's I guess this recent paper was one of the main ones bringing it back in a big way to say, look, it can really do things in practice. It's not, you know, too the barrier for using it is not too hard to overcome. So it's like, although it's kind of messy, it's still usable. Okay, so let's go on to the next presentation, unless there's any more questions. Okay, so maybe we will do, let's see. We can do Zhuangfei next, I guess. Oh, and I should mention, so I am planning to run a little bit over time this week. So if you have to leave early, I guess that's okay. So we will try to end at 45.
Oh, can you guys hear me?
We can hardly hear you. I can't hear anything. I don't know if other people. I can just barely hear you, but
Yeah, I can barely hear you as well.
Okay, I'll try to adjust my microphone.
Yeah.
Is it better now?
Yeah, I think so.
Okay. So hi everyone. I'm Zhang Feihu, and today I'm going to present the second paper, quantum lower bounds for approximate counting. So first, I have to apologize to Sarah because I kind of prepared for the wrong paper. I didn't check the instructions on yet.
Yeah, sorry for the confusion there.
I'll try to deliver. Honestly, I haven't understood this whole paper, so I will try to deliver what I have understood and thought of, and I hope you guys and Sheriff can make some corrections or completions. So this, I first have a brief overview of what this paper. So basically, this paper solves the problem of a lower bound for approximate counting problem. Uh, uh,
Um,
Is it frozen for you guys?
yeah, Jaffe, I think you're disconnected potentially. I haven't been able to hear you. Okay. I guess we have some technical difficulties.
Shalev, do you happen to know,
Yes.
as a professor, when we might be allowed back on campus? Some of us.
Oh. Are you asking about allowed or required?
Allowed. I think that's the one I want.
Okay, I'm not sure. I know more about kind of when classes return, because that's the one I've been following. Yeah.
Okay. Oh, good. Just wanted to ask.
Yeah. So yeah, no, I'm not sure. I think they've now committed that the spring term is going to be online.
Yeah.
So yeah. And they have been what are the thoughts on it?
Okay.
Okay. So can you guys hear me now?
Yeah, I can see you.
I guess my network quality is really poor. So so I'll continue with my presentation. Shall I start now?
Yeah, go ahead. I mean, it's a bit hard to hear you, but that's okay. I'll turn on the turn the volume higher from my end.
Okay, so first let's define the problem of approximate counting. So given a set of S, we should determine the size of this set. After we have known that the size is either larger than 2W or smaller than W. And to solve this problem, we will have a membership oracle for S, and we will answer this oracle would answer if an element is in S. And some tools used in this paper are the Laurent polynomials. So the Laurent polynomials are different from ordinary polynomials in the sense that negative degree is allowed in these polynomials. And the complexity for computing the function f. So this is the QMA complexity involving the product between Arthur and Mary. So Arthur receives a witness state psi from the power from Mary and tries to verify it, such that if this so this product is used to compute the function f. If fx equals 1, then Arthur will accept with high probability for some state psi, and otherwise Arthur will reject with high probability for any possible state psi. And definition of SBQP complexity class. So the SBQP complexity class means that this is also an algorithm to compute the function f. So with these algorithms, if fx equals 1, it accepts with a probability larger than alpha, where alpha is a predetermined value. So alpha is not affected by the content of the input, but only the size of input. Otherwise, the algorithm will accept with probability less than half of alpha. So this, by the definition of SBQP algorithms, it will accept the correct answers with twice the probability of incorrect answers. And about the Q samples and unitary of Q samples. So this means besides the membership oracle we have mentioned, we now have stronger ability to decide to have access to the superposition state of S, which consists of all possible members of this predefined set S. And we also have access to unitary to the unitary to produce this state. And the results of the paper include two parts. First, it gives a complexity lower bound for the QMA product in a problem of approximate counting. And the second result of this paper is that it gave a lower bound for approximate counting with stronger ability. That's the Q samples ability. So it proved that even with this stronger ability, there's no substantial improvement in the lower bound for correct complexity. And how are these concepts connected? So basically, the relationship between polynomial degree and quantum complexity is included in the famous observation that if a quantum algorithm Q makes t queries to input x, then its acceptance probability can be written as a real multilinear polynomial in a base of x of degree at most 2t. So we can use to to estimate the corresponding degree of this polynomial to give a bound for the correct complexity of the original problem. And so the idea of this paper is that it studies a problem called N2 of approximate counting. So basically, in this problem, it considers the approximate counting problem on two separate inputs and AND them and produce the results and give it so the verifier receives the AND of this approximate counting on two separate instances and two separate inputs. So the idea of this paper is that first, according to this symmetrization with two oracles, we can build a corresponding polynomial according to the original oracles and distributions, and we can describe the quantum algorithms with these polynomials. There's two polynomials, P and Q. So P refers to the expectation with respect to the size of parameters, and Q refers to the expectation with respect to the Bernoulli distribution for each bit. So the differences between these two between these two polynomials is that the former gives a bound for only integer values. So P is or initially bounded only on integer values, while the latter, that is, it gives a bound for like all real values, and this is the function that we want. And since we obtained a bivariant polynomial, that we see that in both P and Q there are two variants, so it is hard to estimate the bound for degree. So in that sense, we need to reduce them to univariant functions and polynomials. So how do we achieve that? First, we make the polynomial symmetric, and we will use a simple substitution. So S equals T plus 1 over T. So with this substitution and this symmetrization of the original function P, we can obtain a new function, a new polynomial that's univariant, so that it has only one variant. And according to the approximation theory, first, if the polynomial is bounded at a certain discrete points, we can give a bound for the whole interval. And if this polynomial is bounded for certain intervals, we can extend this interval to get a relative bound for adjacent intervals. So this extension is based on the degree of these polynomials. So with all these concepts, we can now try to derive how this paper gets the QMA complexity lower bound for approximate counting. First, in result 1, they first defined an area which looked like the letter L. So in this area, suppose we have a SBQP algorithm, we can have the following bound for this corresponding polynomial on this area. And suppose that we have a limit for the degree of these polynomials. We could bound P. We could bound P at the lattice points outside of L. So because initially we could bound bound P in the region of L, and now by the approximation theory, we can extend this bound to other regions outside of L, and moreover, we can give an upper bound for Q in the L area. So based on P, we can give an upper bound for Q, and the lower bound at a certain point. So if like shown in this graph, if in all those gray areas, we have a lower bound for we have an upper bound for all the values, and at a certain point we have a lower bound for this value. So based on this, we can derive a bound for the degree of this polynomial, because it has to be the degree must be large enough to ensure that at this certain point the result is large enough. But in all these gray areas, the value of this function is restricted by an upper bound. So this is the results derived by the SPQP problem. And regarding the second method, they achieved an optimal bound of QMA complexity. So in this method, they considered they achieved this bound with similar analysis. In this in the first case, it's just SPQP. The concept of SPQP is no longer involved. So they also constructed a polynomial and used this Laurent polynomial to reduce this bivariant polynomial to univariant. And with similar methods, they use a bound for this the degree of this polynomial. So similarly, they still yielded a lower bound at a certain point and an upper bound at other areas. So at these gray areas, they have the upper bound, but at this point, they have a lower bound. So this with these conclusions, they can derive an upper bound for polynomial, and a lower bound for the degree of these polynomials. And the second result is the complexity with Q sampling. So that QB, the idea of proof is similar to the old concept of tracing. So basically, in this paper, the BBC, in this BBC paper, we know that we can describe the probabilities of a certain quantum algorithm with a polynomial. So this paper tries to extend this idea to Laurent polynomials. So we can describe this probability distribution with not only ordinary polynomials, but also univariate Laurent polynomial. And yeah, the idea of proof is very similar to the original idea. So they still trace the change of this polynomial at each unitary and proof by induction. So there are three kinds of possible unitaries. So the membership oracle, the reflection oracle, which refers to the Q sampling unitary, and independent unitaries. And with this, by analyzing each kind of these unitaries, they can achieve conclusion of the relationship between the query complexity and the degree of this derived polynomial. So with this extended conclusion, they try to with this extension, they try to solve this complexity problem with Q sampling. So first, they gave an upper bound by providing some examples.
All right. So sorry, I think I'm gonna
have to... So two separate algorithms.
Sorry, Jumping. It's just it's getting somewhat late for us.
Okay.
Wait. Hello.
Hi.
Yeah. Like it's hard to hear you actually. So yeah, maybe can you hear me, Jeffrey? I feel like I stopped being able to hear you.
Yeah, I can hear you.
Okay, so right, so yeah, I see you have you have a bunch more that you wrote. Yeah, so I think we have to stop this presentation here, and we'll go to the next one in a minute. So because we're kind of running late. But yeah, thanks for the presentation. Does anybody have any quick questions for Zhangfei?
Okay.
So let me just say a couple things. So as Zhangfei was mentioning, we have so the paper actually uses these Laurent polynomials, which are of polynomials that have 1 over x. So they're not really real polynomials. They have monomials that have negative degree. This is a single variate polynomials of that form, right? And actually, they come up here in 2 different places. So there's kind of 2 different things that the authors do with these polynomials. So it's kind of for 2 unrelated problems. These Laurent polynomials come up, and I believe there's no dual polynomials in this work, so it's basically all effectively just symmetrization techniques. But it's sort of interesting to see that sometimes in quantum query complexity, or I guess these models related to quantum query complexity, where you have extra advice state that's given that you can ask for. That's a quantum state. Then the right object to analyze is this Laurent polynomial that comes out, and you can kind of bound the complexity of the algorithm by the degree of the Laurent polynomial. Okay, any more comments on this paper? Yeah, sorry for cutting you off, Zhangfei. Yeah, so yeah, so in our remaining negative time, for the last, let's go through the last presentation, which is I don't know if you prefer to be called Matt or hello.
Hello.
Yeah, so should I call you Matt or Zheng Hong or?
Yeah, you can just call me Matt.
Okay.
I'm trying to share my screen. Can you see my screen?
Not at the moment.
Connect. I'll redial again. Just a minute.
Okay, so sorry for all the technical difficulties and going over time.
Okay. Okay, so can everybody see my screen? Yes, okay.
Yeah.
Oh, and I will quickly go through the paper today at the classical lower bounds from quantum upper bounds 2018. That a quick overview of this problem solved by this paper is that we try to estimate the approximate degree of composition questions. That is, given a function, how hard it is to compute like the composition of or on the n copies of f. In the lecture, we know some method to estimate the complexity like the parity function or promise over. So a basic way to do this is to estimate two functions like the or and f independently, and we compute the complexity of the product. But that would not give us the lower bounds on such combination functions. So and we quickly review the history from the paper that if we want to compute such question complexity, we could do something like we first limited some functions that we know, like we take the function f as n function, and then we can try to estimate its lower bounds. From the table, you can see that if we limited our discussion to the function n, then we can mildly improve the lower bounds for like 20 years or 10 years. And
Well, I don't
also,
know, but I feel like is your screen stuck? I mean, are you scrolling through the slides and because okay.
Okay, like this. Okay.
Oh,
so okay, another scenario is like we can limit our f to depth to n or 3, like the work I shared and the 2013 paper, and we can discuss the depth d and or 3 on n inputs. And in such scenario, we can estimate the lower bound like here, I list here, like the square nm, and in the depth d or and or 3, we can estimate its lower bound at best like here, this here. And we can also limit the function to the majority function. So we can have the approximate degree like the omega n. And the contribution of this paper is that we try to extend the approximate degree on arbitrary functions. So we have two theorems delivered by this paper that for any Boolean function, we can estimate the approximate degree as like here, this here, the square n times the approximate degree of f. And from this theorem, we can tighten the lower bound like the depth d and or 3 to square n, and the majority function will be like the 32. And also, it is very cool that this paper further proves that for any symmetry Boolean function g and any Boolean function f, we can estimate their approximate degree on their composition, like the equation list here. That would be the omega of degree, approximate degree of Gn times the approximate degree of f. And this paper further discussed the the application to the communication complexity. And we have the three theorems here that, but I don't really understand this part that for its application to the communication complexity, we have these three theorems that is kind of reprove the previous paper from a different point of view. And the advantage of this, or the contribution of this paper is that there's no overcomposition result was known for approximate rank for the communication complexity. And it is like a more direct proof compared to a previous publication. Okay, so the approach of this paper could be listed as follows. That its major insight is that a fast quantum algorithm will somehow imply lower bounds. So this paper majorly relies on the beloved algorithm for combinational group testing problem. And it also used the relationship of the quantum algorithm and the approximate degree of functions. And it is to discuss the composition functions approximate degree. It also used the result from the Shestov robust polynomial construction to construct X polynomials. And then with all this together, and then another result from the Shestov paper, we can compute the XOR combination on the function f, and finally we will get the lower bounds on the composition functions until here. So we will have the overcomposition on function f. And then based on this like major concept of proof, this paper further extends to other parts, like the flow chart here. The center of this paper is the proof steps I just mentioned in section 2.2. And then in order to extend to the major result I just mentioned in theorem 2, we try to estimate the approximate degree of any symmetry Boolean functions times a composition of any Boolean functions. We need a mid step to estimate the approximate degree of promise OR. So this paper, I find the other thing is that to discuss the promise OR composition, this paper mentioned that the major concept used in the OR composition steps, the Shestov polynomial. Here, if we try to extend our idea from OR to symmetry function, we have to tackle some difficulty when considering partial functions. So the Shestov polynomial construction will have some disadvantage, like the polynomial is not nonlinear and the value will blow up. So this paper tries another way to circumvent this issue when constructing the polynomials. That it tries to prove that the polynomial construct from the quantum algorithm is mildly robust and multilinear. So if we can instead use this idea, then we can circumvent the problems introduced by the Shestov polynomial, but we could sacrifice the the tighter loose lower bounds. And finally, this paper also demonstrates some open problems that a conjecture of the approximate degree of any function compositions. We just limited to discuss the symmetry Boolean functions, composition of a Boolean function. Would it be possible that the approximate degree of the all Boolean functions will still have the same lower bound like the question here? And this proof, the proof technique used by this paper is like treating the quantum algorithms, the combinational group testing algorithm as a black box. So would it be possible to prove the result by a dual polynomial method we just discussed? And finally, if the or composition functions is paired with the combinational group testing algorithm, is there other functions beyond OR that could have a paired quantum algorithm that we can apply this kind of black box proof method on it? And maybe we could have some interesting findings. Yeah.
Okay, thanks. All right, any questions for Matt? Okay, so let me just say a few words about this paper. So I guess we've seen paper, so far we've seen a paper that had that used dual polynomials as the main technique, and we saw another paper that used these Laurent polynomials plus symmetrization as sort of the main technique. And here, the main technique is actually, well, it's actually a quantum algorithm. So you kind of prove lower bounds using algorithms. And the idea is, well, it's basically a reduction. But the idea is that there's this quantum algorithm, as Matt said, from that's by Belov, and Belov gave this quantum algorithm for the combinatorial group testing problem, and you know, the point of this problem is, you know, the problem asks, you know, suppose you had access to subset OR queries, so you can ask for any the OR of any subset of the input string, so you can pick a subset S and get the OR of the bits in the input string. So if you were able to make such queries in superposition, how many queries do you need to extract the whole string? And the answer turns out to be root n queries instead of like n queries, which would take you to read the string normally. And this is a bit similar to Bernstein-Vazirani, if you remember that algorithm. That algorithm used subset parity queries to get the entire string with one quantum query, just one query in superposition. To the parities of subsets. And here we're doing subset OR queries. These are weaker, it turns out, but you can still use root n of them instead of n of them to extract an n-bit string. And the idea is that a quantum algorithm turns into a polynomial, so you can convert this quantum algorithm by Belov into a polynomial which does the same thing. You know, if you're careful about how you're doing it, then you have now a polynomial that does this operation, and now you can basically convert anything that computes the OR function. Like if you had a polynomial that computes all OR of n copies of G, so suppose you have a polynomial for that, then you can sort of use that polynomial to compute the subset OR queries that you were going to do, and you can basically extract. Effectively, you can, by composing the polynomials, effectively you get a polynomial that extracts all n copies of G, or the parity of n copies of G, or something like that. So you get a reduction to this other problem, and so you know, you in the end only need to lower bound this new task. So if you lower bound the degree of, let's say computing the parity of n copies of G, then by this technique, you also get a lower bound for the OR of n copies. So if, because this is an algorithm that takes converts the ability to compute OR into the ability to extract the whole string and therefore also compute parity. So because you have such an algorithm, you also have such a polynomial, and you basically get a reduction that says that if you ever prove a lower bound for like parity, then you get a somewhat weaker lower bound, but still a lower bound for OR. And of course, for the actual parity and OR functions, we already have quantum lower bounds and polynomial lower bounds. But here the trick is that it also works for kind of composition of OR composed with G or parity composed with G, and you still get this reduction working. And so this is kind of the point of this paper, is that you can basically prove polynomial lower bounds using polynomial upper bounds or using quantum upper bounds, basically because the upper bounds works as a reduction. It's sort of using neither dual polynomials nor symmetrization, because it's not really using any direct lower bound argument. It's just a reduction effectively. So it's just using an algorithm. So the lower bound that you need at the end of the day was already known. Okay, so thanks to Matt for the presentation. Any more questions on any of the papers? All right, so I guess we'll finally wrap up. Sorry that we're running so late. So again, next week is reading week, but the week after that we'll be back. And I'll post on Piazza regarding the material and also regarding who is presenting in 2 weeks. Okay, so I guess I'll see you then.
Okay, bye.
Bye.
Thank you.